10 years to come back and say, I hope there will be a BTech in photonics. So, we already mentioned in the beginning, I mentioned there are so many things that are coming up. Now let us go to slightly basics. See, now one of the important immediate domains of interest to electronics and the students is VLSI. Because until now, our country is mostly based on software and services. All the jobs are in the software services except like Infosys, Wipro, all these companies are doing only software and services. Not much hardware. Okay. So all the cell phones, the laptops, the TVs, all those things, most of them, the internal, the chips are mostly made abroad, like in Taiwan or Singapore or Hong Kong and so on. Sometimes some companies are there here who are just assembling all these things and then selling you. Just imagine why you have to pay some 70,000 or more than that for a cell phone. Why is it so costly? Is it worth so much? Is an important question. Why is it so? That is because we don't have the technology here. All the chip manufacturing is not here. Okay? So these are all some decisions. Now what is happening? The Indian government has said, make in India. So all these things have to be made in India. In particular, they are oriented towards defense equipment. Defense is a very big budget and compared to consumer. In fact, most of you people don't worry about what is the economy. See, suppose you are a telecom engineer, you should be able to tell us how many telephones are there in India, what is the tele density, what is the government policy on the spectrum. These are all the important things for us which are not there in our curriculum also sometimes. So we should know that. See, at a basic level we know, like everyone has got a cell phone, we are able to see a YouTube or video easily. This is consumer point of view, as a user, not as a technical person. That is important, of course. Then as a technical person, what is important? The tele density, how is it growing, the industry. What are these people, Geo, suppose if they come up with some new plan to make some fiber optics in India, but that's all professional things. We, as an engineer, once you finish your BTech, if you go out, these are things that you should be working. And also a lot of software is there for all these things. Software cannot be discounted. Okay? See, we say that software, only software jobs are there, but not completely true. Gradually, other jobs will come in. Our most important development, you can say, from government point of view, technology point of view, is the VLSI. A lot of jobs are going to be there. Like software earlier, I cannot compare with that because so much expertise is not needed for software. Whereas for VLSI, you need to know a lot of fabrication process, chip design, all these tools, CAD tools, all these things. If you learn these CAD tools, it will be very, very useful for your job purpose. Okay? From technology point of view, chip is going to be important thing in India also. And we may, in future, we may even export to outside. So there can be a lot of devices, electronics made in India and just go to outside. Like what you just compare with other technologies like space technology. ISRO is launching satellites for other countries. Okay. We are providing software services to other places, even US, like Infosys and some of these people. They do services for outside, not more than for ourselves also. So the most important development is on the chip. Then, in the beginning I talked about fiber optics. Fiber optics means you have an optical fiber connecting from one point to the other point, and light waves will take these signals across. So you have to modulate the laser, the light wave, and then transmit on the fiber. That's a simple thing. Point A, point B. Laser is modulated with high data rate up to 10 Gbps. It's possible. Send on the one point to the other. Fiber optic communication. Then you need a lot of terminal equipment. One of the important this thing is called the networking. Suppose you want some 1,000 users are there. How do you connect all these people with fiber optics? Point to point, you understand. Modulator or the source, transmitter, receiver, and fiber. That's all. Whereas if you want to network, then you have to do other components are needed, like switching is needed, routing is needed, and a lot of security is needed. Broadcasting, free space also. It's not fiber. So a lot of optical components are needed. Other is what you have to do. You have to convert it to electrical domain and then the retransmit. Then what happens? The bandwidth is limited. Electronics means the bandwidth is limited. Maybe up to a few Gbps. The Intel chips and all these chips, their maximum speeds are up to gigahertz, few gigahertz. That is the electronic limit. Beyond that, they are not. Whereas fiber optics, you can go for gigabits, 10 Gbps, 100 Gbps, etc. Terabits per second also. They go very high bandwidth. That's why we are able to get the video and all those things on our cell phone. Root cause. So the chip is an important thing. What we want to have? Chips. All the components necessary for a system should be on the chip. That's what is happening in PLC. Same thing we need in photonics. We want to optical engineering more and more. We need to go optical components on a chip. We cannot exactly copy from electronics. We cannot have transistor, optical transistor. You can have some components like switches. Electronic switches are there, you can make optical switches. And also, what else? Conventional optical components, lenses, mirrors, prisms you see on the optical table, they are needed in all optical functions. For example, polarization is an important problem. So you can make a polarizer on the chip. So there are many components that can be made on the chip. Sensors, of course. A lot of sensors are there. MEMS sensors we talk about now. MEMS is the big technology in sensors. Micro electromechanical systems. All are very small in your cell phones and all you have MEMS sensors like accelerometer, gyroscope. When you turn the cell phone from landscape to portrait, the picture automatically changes. How is it doing? It has got a sensor. Rotation sensor is there, gyroscope is there. So a lot of things are there in your cell phone itself. Please read what technical aspects of your cell phone or whatever laptop. When you click some file here, when you are sending some picture from photo from here to your friend, what is happening? If you search, you will know all the ECE technology. I would suggest students to try that, and also some expert from other faculty members can tell what is happening when I want to send a photo from here to your friend. What are the various technical things that happen, including the protocol, then your 5-7-layer model. Everything can be explained by using such examples. People want to know actually, not simply what is there in the book. Of course, they are correct. What is there is very accurate in a systematic manner in this book. But from our point of view, we want to learn what we want to pick up specific things, not everything. For the exam, you study everything. Don't skip. Okay? See, you say that that's not so important for me. Then I am coming to the point that we need to make a chip in the optical domain. Optical switches, modulators, and so on and so forth. We need it optical. It's very crude right now. In VLSI, you can make thousands and millions of transistors on the chip. We cannot make such things in optical. But what will happen? How they will become? By very simple examples, I will show you one or two. So I will show you some passive devices, some active devices, then some applications to communication sensors, etc. And originally I thought I will show all these things later once. These are the emerging topics. For those who are really interested, later on can have a good workshop on. See, there are all these. There are 3 important emerging domains. Just for those who already know, micro resonators, photonic band gap structures, and waveguide gratings. These are the three important topics in the emerging for those who want to do research and so take up projects and so on. So that will not use so much. 1 or 2 examples I tell you: a modulator and some applications and some passive devices. This we have already seen earlier. In the beginning, I said that we can do a lot of things with photonics. You can generate. See, in electronics, we do all these processes. We generate signals. You have. You can control. Then you can transmit from one point to the other. You can do signal processing. You can display all these things. Then same things can be done with photonics. You can generate light signals. You can control them. You can transmit. You can display. One important thing that you cannot do is to store. Memories are difficult in optics still. Memory is an important element in electronics. Several gigabits, terabits of memory you have on your cell phone, but there is no memory in photonics. So it is mostly useful for processing. So in fact, when you say storage also, of course now we have flash stamps, but the memories are all like the magnetic and some other physical things, not really flash stamps. only some RAMs and such. Certain small portion of your memory is electronic. So let me show you pictures only, not stories like this. So these are some examples. N by N switch area people have made. Then fiber optic gyroscope chip. Gyroscope we just not talked about. This is about professional thing for aircraft and the defense purposes. We have made this fiber optic gyroscope chip in our lab. That one. Then micro optical bench. Whatever you see on the optics table in the optics lab, people have put it on a small silicon wafer. That is called micro optical bench. Entire optical bench in size can come to 1 centimeter. That is already done by people using MEMS. So this is an example of a modulator, high-speed modulator. If you want to go for 10 Gbps, you have to use this. You are seeing the top view of a lithium niobate modulator. So this crystal is called the lithium niobate. That's a crystal like glass, quartz, etc. But it has got a very good property called electro-optic property. You can change the refractive index if you apply voltage. See, if you apply voltage, can you change the refractive index of some material? For example, A you cannot change. Glass, if you have, you cannot change the refractive index easily. Water you cannot change. So there are crystals whose refractive index can be changed. These are called electro-optic crystals. So you take an electro-optic crystal and make this pattern. This is called the MZI, Mach Zehnder Interferometer. It has got a Y branch. You see all the double lines that you see are waveguides. Waveguides means light will propagate only in that, not outside. And if there is a Y branch like this, the light will be split into two parts. Half the light that side, half the light that side. That is called the Y branch. Then there is a Y combiner. On the other end is a Y combiner. When two light waves are coming, they can be combined into one waveguide. And you also see two blue patches. So blue patches are electrodes. You can apply voltage on that and change the refractive index. So this is called an MZI. So if you launch light to the input of this MZI, it will divide into two parts, propagate through those waveguides under the blue patches, and then recombine. So when you apply voltage on blue patch, what happens? The refractive index changes. So you must remember at least one small equation to understand properly. E power I omega t minus beta z. Most of you know, is it not? E power I omega t minus beta z. Beta is one which contains the refractive index. 2 pi by lambda into refractive index. So if you change the refractive index, you are exponential changing. That is phase modulation. You have come across phase modulation in the college in your second year, is there or not? So you are phase modulating the light wave. You simply imagine, don't worry about the physical part. Simply imagine A sin omega t minus beta z. And inside the sin omega t, you have the phase beta, that is phi, plus phi, you can think of it. So you are phase modulating. So once you are doing the interferometer, you are adding two sin omega t's, sin omega t plus phi and sin omega t. Then it becomes amplitude modulation. So the light wave amplitude will change according to the voltage that you put. So you can put a voltage of RF high frequency up to some gigahertz, 10, 5, 10 gigahertz, you can easily put on that electrodes. So you can modulate the light wave with this 10 gigahertz RF baseband signal. So that is the idea behind this modulator. Okay? So the basic to that is electro-optic effect. You should be able to change the refractive index. So it has got very good properties. Very low voltage needed. Only few volts is needed for modulating. Then you can go for 100 Gbps also. Of course, not this configuration. For those who are interested, those are the microwaves. I can say that these two will be called microstrip lines. Those two patches are microstrip lines. Microwave will propagate on top of that, and light wave will propagate in the waveguides, and the interaction between them will create very high speed modulation. 100 Gbps, high speed modulation can be done with this. One more example. This is called a directional coupler. There are two waveguides very close together. So typically these waveguides are 4 micrometers width. That crystal lithium niobate design will consist of 4 micrometers width. Light wave frequencies or wavelength is 1 micron. Optical communication band is 1.5 microns or 1530 nanometers to 1560 nanometers. Visible light is 400 nanometers to 700 nanometers. That is still less than 1. In optical communication, we talk about 1.5, okay? Not visible, it's infrared. So typical dimensions are 4 micron width. And a gap also I am showing you 4 microns. diffract index difference. Suppose you put electronic effect, diffract index will difference will be 1%. 2.1 is the refractive index of lithium niobate. It can become 2.11 or something like that. Very small. 1% is enough to make a good modulator. Because we should always talk in terms of numbers. In engineering, we want to know numbers, how much temperature we should heat, or how much voltage we should apply, etc. Sometimes when you calculate, you get 100 volts for the electrode. That's not practical. Okay? So when you bring two electrodes close together, light can tunnel. You apply light, you send the light from the first port. It can come out of the fourth port. If you apply light in the second port, it can come out of the third port. That means if you apply two signals S1 and S2 at the input, they can become S2 and S1. Cross state, exchange, like the exchange between the ports. Okay? How does it happen? That is because of the gap. Normally, you use Snell's law to study all these fiber optics. Snell's law means total internal reflection. Is it not? If the light goes from higher medium to lower medium, after a critical angle, the light will reflect back into the same medium. So, light will get trapped in the optical fiber, it goes from this end to that end, several tens of kilometers, 100 kilometers it can go. Similarly, in optical waveguide also, light can get trapped and go from this end to that end, but only 1 centimeter or 1 millimeter. All the chips are very small, okay? 1 centimeter typically. But only difference is fiber optics. This is fiber optics is circular cross section, like a hair. Okay. A typical optical fiber is as thin as your hair, some 100 microns total. Actual core, where light properties is only 10 microns, not so much. Here also the wavelengths are 4 microns, small. Outside is the crystal slab. So light will get trapped in. But when you bring two wavelengths close together, by wave phenomena, the light will tunnel. You cannot explain it using the geometrical optics. Snell's law is not valid. You must go to wave equation. Anyone has this? Somehow they have electromagnetics or something in the second year? Sometimes you maybe it's of course I know that it's a tough subject. You have to study electromagnetics, electromagnetic theory or field theory. Don't worry about all electrical magnetic fields, but finally the wave equation, how the wave propagates, you know this. Or simply for the time being for today, you just remember e power I omega t minus beta z. But if you bring two wavelengths close together, light can tunnel. That comes with the wave phenomenon, boundary conditions and all that. Or let me, because they are all electrons, let us take another example. Like a tunnel diode. There is a potential barrier. One side one layer, other side another layer. In between the layer where the band gap is high. So the light can tunnel. The electrons can tunnel from other layer to this layer, even if there is potential barrier. Okay. Similarly, even though there is a low refractive index in between, the light will tunnel. It will not reflect back. Okay. That is the phenomenon. All is what is the tunneling, you can say if you want. Then what I do is I put voltage on top of that and change the refractive index so that it will tunnel in the first half and goes back. So S1 will come out as third port, S2 from the fourth port. This is called the crossover state or bar state of the switch. S1 is to become S2, S1 crossover state. S1 goes to the first port again, S2 goes to the second port again, it's a bar state. So by putting voltage on top of that, switching voltage, you can switch between cross state and bar state. This is a multi-purpose device. You can make AND gate, NOR gate, and 3D couplers, optical switches. Many things can be built from this. This is the general purpose of photonic device. This we can fabricate. In ISC, if someone wants to fabricate, you can come to our lab. But more sophisticated things can be done. I am trying to simplify as much as possible. Typically, this process is called titanium diffusion into lithium niobate. You take a titanium strip metal and then diffuse for about 8 hours. Some how much concentration? 1% concentration. You will diffuse at a temperature of about 1000 degrees centigrade, 800,000. That is a lithium niobate process. There are other easier processes like silicon. Many of you know that silicon is the most popular material for VLSI. So on silicon also we can make optical waveguides, optical devices like this interferometers and all. This is called silicon photonics. People think that silicon photonics is the next step of VLSI. If someone is interested in VLSI, next step after silicon is called the silicon photonics. People use optical interconnects to connect different processors, chips, and so on. So these are all various features of photonic ICs. They are very small. They can be controlled. They are based on the single mode operation. That means you cannot use the geometrical objects. Then you can produce large numbers, very cheap. These are all the advantages, like VLSI you can say, and low voltages. So history we already talked about. Since starting from 1960s, all these new things have developed. 70s is the era of optoelectronics, semiconductor devices. 80s is the domain of systems. Many fiber optic systems have developed, including in India. 90s is the era of networking. Internet has come, and people have started what is called this WTM, wavelength reduced multiplexing. Then after 2000, people have concentrated more on the hardware side. MEMS is an important development in 2000s. In the last 10 years or so, people are more and more applications rather than fundamental. Of course, a lot of developments are there in VLSI, but people are looking at more and more applications now, like IoT, sensors, and all those things is the main focus now. But once again, I hope in this 20s and next 10 years, people will go back to more and more hardware. In the VLSI itself, then gradually comes the optical VLSI, photonic ICs. So about 10 years is there for this, you can say. So I show you some waveguides, cross sections of waveguides. How does a waveguide look like? As I mentioned, you take a substrate like glass, diffuse. Glass has got sodium, you diffuse silver. Then it comes only selective diffusion. You must put some mask, aluminum mask, remove the aluminum, but wherever you don't want, wherever you want to diffuse silver, you get a muddy waveguide. You can also make a ridge waveguide. You can put some other material on top of that, like polymer or something, etch out unnecessary regions. Chemical etching is called. Then you can load. You can put an electrode on top of that and put voltage in some crystals, like lithium waveguide. You can make an induced waveguides. So there are many ways to make optical circuits. So this is a broad technology. So many materials are there, like silicon, gallium arsenide, magnetic materials, glass. For very low cost glass can be used. Polymers are coming up. Biomaterials are needed if you want to make biosensors. And then corresponding technology we have to choose. If there is semiconductor technology, we have to use diffusion, impedance growth. These are all the terms, terminologies. Don't worry about it, you don't understand all this. You take some simple paper on whatever subject like photonics or PICs you want, read that, you will easily know. That one I can give you also, depending on your interest. I would suggest in the photonics chapter in your college, because they have, see, don't take everyone to be equal. You ask individual students what you want in photonics also. By the time they finish their third year, you can say that you can conduct a couple of workshops, they will be very comfortable with photonics, including mathematics. You should not do only hands-on software typing. Okay? You do a program on waveguide theory where you will solve the wave equation in the class. You show how to solve using MATLAB or something. You can easily do that. I don't underestimate yourself. I would suggest, I hope you are able to get the point, is it not? Many students, you are worried about mathematics. Only block diagram you want, or keyboard, some drop down menu and then take that and simulate, generate some graph. No. If you want to understand really, you have to go to mathematics. Please brush up your linear algebra or transforms or differential equations and so on. In fact, in IIT Bangalore section, we are thinking of conducting one crash course in mathematics, some 2 days. All the 4 areas, 4 or 5 areas that are important for whatever branch, we can revise in 2 hours. Linear algebra for 4 hours. Either we want to revise. Please come forward to hold such programs in your college also. We can post it here. And students, please tell us. We have one difficult subjects seminar series, tutorial series, difficult subjects. Suppose like a control system is difficult for you. Tell us. We will conduct one tutorial here. Not only for you, for all the students in Kannada. So we have a program on difficult. Vemana Institute has come forward already to conduct on electromagnetic theory. Sometime I don't know when they will conduct. Please come there. Electromagnetic theory is difficult for you. Whole day, only electromagnetic theory. Okay. Such programs we want to conduct in ITP. That's why you should be an ITP member. I hope you have an ITP board. Notice what is there? ITP in your college. Please put all these things, whatever we are trying to. Okay, let's go. So I'll show you some passive USs. So it's very easy to appreciate. Don't need any mathematics right now. Y branch, you divide the power into two parts. 1 by 3 coupler, you divide incoming power into 3 parts. If you launch 1 milliwatt, half milliwatt will come in the first one, half milliwatt in the second one. Similarly, directional couplers also you have seen. Okay? But there will mathematically, there is, if you are doing a project, if you want to understand, if you want to analyze, if you want to simulate, there is a problem here. I suppose some of you have understood. There is a corner, sharp bend is there in the Y branch. That is not easy to solve mathematically. Okay? I don't know whether you realize or not. I'm showing only a picture, so it appears to be easy. You need the theory of complex variables to solve this problem. Tapered waveguide. Along the direction of propagation, you have an increasing width. For that, you see, wave equation is a differential equation. If you are not scared, I will tell you. Wave equation is a differential equation. If you have a taper, you get a differential equation with variable coefficients. If there are constant coefficients, you can solve easily. If there is variable coefficient, there is a problem. Okay? Please tell us, please respond. In between also, please stop and ask. I will tell you something different if you want. Okay? That's why I want one active student member to sit here. I will ask him. And his doubt is everyone's doubt. Otherwise, I will only be speaking. I don't know whether you are really understanding or not. Sometimes I may be speaking at a very low level. It's very easy for you. Please tell us. So these are called directional couplers. They can change the direction of light that is propagating in the waveguides. Star couplers are needed if you want to distribute the power across different users. Many input users, many output users can exchange power. How to do is a different problem. Then polarizers. Light is a vector. You have horizontal polarization and vertical polarization. So you can convert from horizontal to vertical polarization. In conventional optics lab, you put a thin crystal slab and change the half wave plate, call it. You change the polarization horizontal to vertical. Similarly, if light is propagated in the wave, it can change. The crux of the problem here is anisotropy. Anisotropy means light will propagate in different directions with different speeds. Different directions with different speeds. So that's the property of the crystal. So you can make polarizers. Many of you would have seen the crystal on your book. 2 images can be seen. Or in the movies, you must have seen the 3D movies, blue and red. One will capture the horizontal polarization, other will capture vertical. In the brain, they will superimpose and you get a 3D effect. So muxes means many channels are coming in the input port. Many channels with different light signals. At lambda 1, lambda 2, lambda 3, lambda 4 signals. Each one can be modulated 110 dBps separately. And they're coming. How to separate out? It's a question. Like the white light problem. You can split the white light into all its colors by using a prism. Similarly, 4 channels, you get all 4 channels can be separated out by using and showing a grating based things. If you put a grating, it can separate. 4 gratings are used. First grating will capture the first channel, second grating, second channel, and so on. 4 channels can be separated out. So this is the idea for mux. Demux. Mux is the opposite of this. Lenses. You can make lenses on the chip. Many of you know about lenses. Your eye glasses are there. You can make them on the chip. They are called geodesic lenses. You have to make an impression. You can strain the crystal. You make a slab waveguide. Top of that, you with a very heavy, some metallic surface, you stress and it becomes a lens. The lenses you can make on the chip. Similarly, graded mixed lenses. You can make pattern. By lithography, you can change the width of that region, and you can make what is called Fresnel lenses. Gratings are of course useful in many ways. I said grating in the beginning for splitting, selecting like a filter. Grating can be used as a filter. It can be used as an input-output coupler from fiber to the chip. Integrated output chip. If you want to get light, what you use is a grating. And the lasers also they use gratings. Nowadays all the lasers are based on the wavelengths. So you will put two gratings. So this is another grating, more complex one. So I will show you one of the dynamic devices. Dynamic devices means control. Until now they are all passive, no control. So this is called a thermo-optic device. You can apply heat on the waveguide and change the refractance. Little bit. Thermal processes are very slow. So you can for protection or for small adjustment, mechanical adjustment is still slower. See, when you want to get some fringes in some electrophotometer, you keep on adjusting. So that is mechanical. You can do thermally or electrically also. So electro-optic we have already seen, modulated. You can change the refractance. So they are all electro-optic devices. Acoustic-optic, you can put a stress on the crystal. You can send a sound wave or stress wave, and then you can change the refractance. Many of you would have experienced in the railway track in the villages or out of cities, when the train is coming from a long distance, you put your ear on the railway track, you can listen to the sound of the train coming. From outside you cannot listen, but from the railway you can listen. That means the sound is propagated in the metal very fast. Sound wave is very, very fast in metal. Similarly, you can propagate light wave in the sound wave in the crystal, and then you can create gratings. So when you send sound wave, what happens? There is a change in the amplitude, and refractive index will change with the stress. Stress-induced refractive index change is called the acoustic or elasto effect. So a lot of uses are there. You can make gratings. You can create optical signal processing. You can do using acoustic effect. So typically what they do is you have alternating plus and minus voltages. The one you can see. In one electrode you have positive voltage, other one negative voltage, and series of that high and low. Refractive index is delta n plus and minus, delta n plus and minus. So it is a grating. There is a periodic change. It's a grating. In normal grating you think in the lab. So there are lines. That means there is a periodic change in the refractive index or height. Then that will act as a grating. So magnetic devices. So you have to have magnetic materials like garnets, lithium aluminum garnet, lithium iron garnet. These are the materials which have magnetic properties. You can apply magnetic field and change the refractive index. And then through refractive index, there are other things can be changed. So you can create a lot of polarization dependent devices. You can create. See, you know, light has got electric and magnetic field. You can control the magnetic field also. Non-linear effects. So some crystals have non-linear properties. That means if the intensity of light is more than some value, it has got a different same light wave. You are passing light through that. If the intensity is more than 5 milliwatt, its refractive index changes. If it is low, its refractive index is different. That means the light that is going on will control itself. So you have to go back to the mathematics, dielectric properties of the medium. Medium is dielectric. So you can relate it to susceptibilities or the electric fields, and it's non-linear. So you can create second harmony. For example, if you send light of 1000 angstroms, or what is it called, 1 micron, then you can create 500. Green light you can generate. So by non-linear effects, you can know all these things. Some systems I want to use fiber optic communication system. 4 users are there, 4 inputs and 4 outputs. You can exchange light between any of these. I am extending, I am just cascading the 2x2 switch that I showed earlier. If you connect like this, from any of the input ports, you can connect to any of the output ports. Okay? All combinations are not possible. First one I will put the cross state, second one the cross state, Last one, the cross check, you can get first one to the last one. You can work out very easily what is that exchange process. All combinations are not possible, you can see. Like the olden days of telecom problem, we want to get full connectivity. How is it possible? How will you connect? It's an important problem. So this is one RF spectrum analyzer. I use lenses and gratings and I can split the incoming signal. Suppose I get some light signal from some star or some pulsar. So we want to know what are the components that are there in this. So you can use this RF spectrum analyzer to split all these things. You can also do a lot of signal processing. You can correlate. You can apply signal, RF signal to the gray, another RF signal to the light wave modulation. So S1 and S2 you can find out the correlation and all such mathematical properties. You can do matrix multiplication. You can represent matrices. You can represent matrices contain the elements as a light signals, and then you can do matrix vector multiplication. Inverse of the matrix you can do. So such computing, optical computing they call, can be done with or in this like these circuits. So this is an optical gyroscope. Chip for an optical gyroscope. Actually, the small coil that you see is the actual gyro. You take an optical fiber coil, rotate, turns, many turns, and then you send light from the clockwise direction and anti-clockwise direction. So one light wave is going in the clockwise, one light wave in the anti-clockwise direction. The delta phi, the phase difference between these two, delta phi is proportional to the angular velocity. That is the idea behind the fiber optic gyroscope. Okay? If you put this on a missile or aircraft or somewhere, when it rotates, it can measure very accurately what rate that is rotating. So, the missile going very straight, it can deviate slightly 1 degree, even if it deviates, we can get a very good signal. So, this is called the fiber optic gyroscope. If you want to build a gyroscope, you require all the other components like polarizer, waveguide, modulator, and power divider, direction number, all these things are needed. So earlier people used to do using fiber optics. Now we can do integrated optics, chip like this. This chip is going on now, we have done it in our lab long ago when I was a student. The fiber optic gyroscope. Then the fiber optic gyroscope is a real device now. They are in the defense labs. The DRDO, they are using it in our designs, like North 3, Agni, they have this fiber optic gyroscope. And the chip they used to get from Russia earlier, Israel, Russia, these people used to say, sell them. Now they are during 2000 tests, there was sanctions on India, they are not selling us. Even lasers they were not selling to India. Of course, now the economy is better, but our people have made our own gyroscope. They can make every day one gyroscope they can make. It's not an easy thing. Alignment, so many problems are there. But still they are making. They will save around 500 crores they are saving every year. Some importing, making in house. Okay. That's a very good device. A lot of examples are there like that in India. This one particularly we made in our lab. One scientist was deputed to work on this fiber optic gyroscope in our lab when I was a student. Then later on we made this. Later on we took a project from DRDO. We made this lithium. This also made of lithium, but different process, not titanium. So Japanese were very much fond of this disk pickup. They want to long ago. Now of course it's not very popular. You can retrieve. See, the optical discs were there. You store large quantities of information, videos and all that. They can easily retrieve using this device. That's all about the basics, literate, just without much mathematics. These are the emerging topics, ring resonators. You make the waveguide in the form of a ring, and the light will go round and round, and very good resonance characteristics. Resonant frequency, very accurate compared to what is the radius of the ring, waveguide ring. And then there is a bus waveguide there, coupling from bus light to the ring. They are all very good properties of the ring resonators. And it is very compact. All the earlier devices that I showed are very long. This is much more compact. A lot of applications. These are all the mathematics of that. Another important current topic in photonics is called the photonic band gap structures. As an example, you create on a silicon wafer ports or shape. So they will act as a very good photonic band gap structures. Like silicon, some silicon band gaps. You have valence band, convex bands, etc. Ions are periodically arranged. So you have convex bands and valence bands. Similarly, you have convex bands and valence bands, but for the light frequencies. Some frequencies can propagate, some frequencies cannot propagate. Make use of this, you can make many devices. I'll show you one example. This is the characteristic, transmission characteristics of the photonic band gap structure. That means the band is not allowed to propagate. So you create defects. In silent semiconductors, you create light defect, point defect, etc. so that they will act as a resonating points. So this is the 4-channel filter. So this is a wavegate on the one line if you move, that will act as a wavegate. One point defect you create, it will act as a resonator. So we use 2 wavegates, one straight wavegate and one perpendicular to tap the energy. So you can have the below you can see the filter characteristics. 4 channels, you tune the cavity or the point defect such that you get a different frequency. So you can make 4-channel home filter like this. One more application. This is called the MEMS, optical MEMS. You can create mechanical components, optical components, and electronic components on the same silicon wafer. See, most of you are, if you are electronics engineer, you thought, what is this? We are not bothered about mechanical. Okay? But in the applications of sensors, we need to know a lot of mechanics. All the physical quantities like pressure, vibration, all these are mechanical quantities. How do we deal with them? We have to learn a little bit of that. So, MEMS devices can respond to all these things. You can integrate only one small chip. I'll show you an example. So these are mirrors. People have made small mirrors on the silicon. So there are various types of optical MEMS people have made. This is one MEMS pressure sensor we made in our lab. We have a silicon wafer. You etch out a diaphragm like a tabla. On top of that, you put the pressure, and then you have an optical layer first on the top of the silicon. Interferometer. Earlier at the beginning we talked about interferometers. We made an interferometer, and one arm of the interferometer below that we have etched out this diaphragm. So only one waveguide is affected. Other waveguide is on the silicon. So this will take the load. So this will, when this vibrates, this will bend, and refractive index will change, and so on. And you can measure the pressure. That is the basic idea in this. This we have done with one of the students. This we have done this optical pressure sensor. Next. That's all I think I have mentioned for today. So I think I have given a little bit of basics and also some new topics. You please go back. When you go back home, you see what is the, of course, you click on your internet or Wikipedia or somewhere to learn more about photonics. I hope most of you are photonics members. Otherwise, please join and they will conduct. You ask them what topics you want to learn, and then they will conduct the programs like that. They will call me. When you call experts, you should say our students want this, not say whatever I want. The speaker, sometimes you must choose the speakers, but you should tell what you want to your students want. The student, actually, that's an important problem I am trying to address right now. Okay? The students should tell us what you want. According to that only we conduct the program, not whatever we want. That's the important part that we have to do in future. And similarly with faculty members, actually there's a lot more potential with the faculty members. They are almost silent. In most colleges I saw a few faculty are very active, but all of us are almost silent. They are doing their job for good teaching and evaluation and all those things, but they have a lot of knowledge and it's going waste. Many of them would have done PhD in some strong subject and no one knows about them. You should bring out, opportunity to go to the FPPs, conduct some programs like this, and so on and so on. It's a recognition for them also. See, someone will say that who is expert, she is expert in this subject. So I hope the student branches will take up programs which will be more useful to the students, which will recognize the faculty, and also we will also convince the managements saying that this is a very useful thing. Otherwise, they will say what is that you are doing. Exams are there, or placements are coming up, and so on. Those are, of course, important degree. But that's how, see, many of the universities, including IIC, very low in the global rankings, 150 or so. IITs are beyond 250. Why is it like that? Because of this problem. We have to address some important things. We should attract foreign students. Then we should go to outside conferences. That's how our rankings will improve. I think it will happen soon. See, first step I think what will happen in our education is they will invite foreign universities to India. They will ask us to collaborate. For example, your college will tie up with some top university, Stanford University or somewhere. I don't know, even too ambitious, but some good university will tie up. Then some of you will be able to go there to do the projects or get some collaboration or do some workshop with them or conferences with them. So that's how our universities will become world class. So for that, we have to do something. If you keep quiet, it will not happen. So thank you very much for listening. Let us make use of our extra effort. About 5% or 10% extra effort is sufficient to make our college top. I would suggest, I don't know, because these are the first year still, let us target to make Vidya Institute the Stanford University of Bangalore. Do you want to make it or not? I suppose many of you would have thought to go to IIT, is it not? Before when you joined BTech, you must have written JEE and wanted to go to IIT. So try to do it. There's nothing wrong in the college. Okay. They have a lot of money and expertise and all that, but all colleges are good. Depends on how you study and okay. Thank you very much for listening.
Thank you, sir, for enriching us with your knowledge about photonics and giving us a deep insight into all the optoelectronic devices. Moving on to the next session, I now call upon Dr. Vani VP, Associate Professor, Department of PC, to introduce our second speaker for the day, Ms. Kamakshi.
I'm Vani VP, Associate Professor, Department of ECE. I'm privileged to introduce our speaker of today's event, Kamakshi. Kamakshi, research scholar, Department of ECE, Indian Institute of Science. She has completed her graduation. She has completed her graduation in Narayana Engineering College, Nellore, 2050, and completed her MTech at SVIT College of Engineering, Tirupati in 2020. Currently, she is pursuing PhD under Srinivasan sir in Indian Institute of Science, Bangalore. Her research area is biophotonics, and she is working on designing of biosensors with cladding as a biolayers using a photonic integrated circuits. The devices explored are slab-bridge waveguides, MRIs, RR, etc. in the software simulation tool in human body. She has presented her work in SPITE Advanced Biophotonics Conference 2021 with the title of Moving Transition Metal Dipolarize assisted with SPR biosensors in a rapid reduction of fluorine glucose. She is a very active IEEE member and she is a vice chair of EMBS Photonics Combined Chapter. She is a part of executive committee member IEEE IASC student branch and is organizing committee of Japan Kappa Tech Fair, which is the largest info Japanese tech event in India. Participated more than 1,400 people from the academics and the industry. She has also participated in the International Light Day event and volunteer in organizing the event. She has also participated in many of IEEE routine training activities. I thank her for accepting our request and being a speaker for today's session. Thank you, madam.
Thank you, ma'am. I now request our second speaker for the day, Ms. Kamakshi and Celebrate Together.
today my topic is optical biosensors. So today I am going to cover about what is the biosensor and what are the different type of biosensors which are available now and what are the current trends and future scope. So let me start with what is biosensor. Biosensor is a device which measures the biological reactions and convert that signals and detect the concentration of analyte. So there are different type of optical biosensors. So this is how the optical sensor unit will be. The first one is the biosample which we will be playing on that device. The other will be the biorecognition molecule which detects the analyte concentration, and the other is a transducer, and the other is the data processing unit. The biosample might be something like glucose or some type of gases and all. And once we apply that, there will be the recognition molecules on that, and it will react with that, and it will generate the equivalent signal based on that reaction. And this transducer will convert that into the optical signal, and you will get the output. The amplifier and data processing unit. So there are different type of optical biosensors which will be bifurcated depending upon the biosamples, depending upon these recognition element based on the input which we are giving and based on the technology. Based on the bioreceptor and the analyte, there are like electrochemical sensors and the optical biosensors. And based on the transducer, it's like electrical and optical, and there are different. I just mentioned the two different types. And based on the bioreceptors, there are different things like enzyme based, antibody based, like that. And based on technology, there are like SPR based and nanotechnology based. These type of biosensors are available. So basically, when we are designing a biosensor, what are the main characteristics we will observe is how the device linearity and how the sensitivity, selectivity, and the response time. These are the main basic characteristics. Let me discuss one by one. The first one is linearity. Like linearity of the device is nothing but how consistently it was measuring the data and how we are accurately getting the output. That depends mainly on the linearity. The other thing is sensitivity, means how much the variation in the output depending upon the concentration is nothing but the sensitivity. While designing any devices, we have to check whether the sensitivity was high or not. So basically, why everyone are moving towards this photon-based or optical-based biosensors means the sensitivity is the main parameter which is crucial while designing a sensors. So as it is offering the high sensitivity, one is slowly preferring the optical biosensors. And the other thing is selectivity. Selectivity is nothing but how wide range it will be having the good accuracy and how we can differentiate the values. Suppose there are like the numbers are 1, 2, 3, 4 in that very thin, minute nanoscale of decimal fraction. Even the sensitivity should be that wide range. It should support the very the output and how fast it was processing the data. Applications. These biosensors is having huge applications in medicine and in environmental and in food and agriculture based things. In medicine, there are different type of optical biosensors which are available, like for measuring the glucose, for detection of cancer, and for detection of different RBCs, WBCs. These kind of biosensors are available. And in agriculture also, there we can monitor the how the quality of the soil. These kind of thing can be done by using these type of biosensors. And coming to food industry, we can check the quality of the particular product by using these biosensors. And coming to environmental means, generally there were this has huge application in mining areas. In those areas, while they are digging anything and doing, will be getting the hazardous gases over there. So these type of biosensors will be used as an application over there. Like it should detect what are the harmful gases which will be coming when doing the process of mining over there. So it is having wide range of application over there also. So now I am discussing the within the optical biosensor itself, there are different types of biosensors, which is like absorbance based, like it was the sensing technique through which we are bifurcating. So in absorbance based biosensor, what it will do is it will absorb the light when some chemical reaction is happening, when the analyte interact with the bioreceptor, and based on that we'll measure the output. That is absorbance based biosensor. That is a fluorescence. The fluorescence is generally a label based biosensor. In that there will be fluorophore. It will detect the it will detect the electrochemical reaction over there and generate the optical signal based on that. So the other is refractive index based sensors, which is widely in application in which we are doing the research in that area. So in refractive index based biosensor, what it will do is when we are applying any analyte over the optical biosensors, so that analyte will causes the refractive index change over the particular device. So that refractive index change will be measured, and we, based on the value of how the refractive index is changing, we will measure the concentration of that particular content, I mean like glucose or something like a gas of methane, how much it was, we will measure based on that ineffective value over there. So generally optical means these biosensors were used in the wavelength range of visible and IR range. So generally the visible range is between 400 to 700 nanometers, and the IR range is still 1 millimeter range. So we have different materials like silicon dioxide, silicon nitride, and there are a few other materials like the lithium niobate. These are the general materials which will be exploring while fabricating any biosensor. And generally I mentioned only 3 here as we are working with those materials, that's why. So each and every material is having a particular refractive index based on the operating wavelength, like what is the operating light which we are inputting to that particular device. I have taken the wavelength of 0.63, and these are the corresponding refractive index value of those materials. So these are the generally available optical devices from the literature papers, like the simple waveguide based biosensor. The other is the Metzeler interferometer based biosensor, and the other is ring resonator based biosensor, and the other is the directional coupler based biosensor. I am touching each and every topic elaborately in the coming sections. So let us see what is the principle behind the working of refractive index biosensor. From now onwards, whatever the biosensor I am discussing, everything is based on the principle of refractive index sensor. So you can observe from the figure like there are three layers, which is silicon dioxide, silicon, and the upper layer is the analyte. Means where we are measuring the concentration of glucose. Let us first suppose right now we are taking glucose as the analyte over here. This might be replaced with anything like methane gas, like so. So when we are guiding a light over the silicon layer, when it was traveling from input to output throughout the waveguide, when it was directing, a part of it is leaked into the substrate and it will leak into the cladding region. So this leaking mode is nothing but the evanescent field. The sensing principle is like when the analyte reacts with this evanescent field, it will changes the refractive index of the device. So based on that refractive index, we will measure what is the concentration of the particular analyte. So this ineffective value will be dependent on the concentration of the analyte which we are applying. It will change equivalently based on that concentration. So this was the Mach-Zehnder interferometer. In this, the phenomena is like there will be two arms and we are inputting light through the Y splitter, and then it will be directed towards the two arms. One will use for sensing the analyte, which is nothing but the sensing arm, and the other is for reference, and the output there will be a Y combined. So when light is directed through it, and it will react the analyte applied over there, and based on that reaction, it will change the ineffective value of the overall device. So based on that ineffective change, it will create the phase change of the Mach-Zehnder interferometer. So based on that, we will detect how much concentration was there in that glucose which we are applying as the analyte of the device. So this is generally the transmission spectrum. We can observe from the figure like for different concentration of glucose, the transmission spectrum is different. So the other device which we will be exploring is the directional coupler. This is a integrated device which is separated with a particular gap. When light is traversing to the waveguide, it will be coupled to the other arm. There are two arms, like one throughput port and the other is cross port. So when the analyte is applied on that, and it will change the ineffective value of that device, and due to that an effective change that can be converted into the intensity change. So in that way, the intensity will give how much concentration was there on the particular biosensor. Like for supposing if a person is having different levels of diabetes, and if we are applying the blood, and we'll measure the concentration of the glucose, and we'll convert that value into the ineffective terms, and from that we'll get the intensity, and based on that intensity we'll detect the glucose levels. So the other device which we'll be exploring is ring resonator. So a ring resonator is having the wide application nowadays. This ring resonator works based on the shift of the resonance speed. That is when we are applying the analyte on the particular particular ring. So based on the concentration of that, the ring N effective will be changed. That N effective value will be converted into the output of the device and will measure how much concentration was there in that particular analyte. So the other device is on photonic crystal based biosensor. So this device is nothing but we are creating holes or not kind of defects in a substrate, and we are applying the analyte over that. Yeah, you can observe in the figure like there are different type of defects which we can create on the particular photonic crystal. That is the line defect and the circular point defects and all. So we'll apply the analyte within that defects, and based on that analyte, the concentration of the concentration of that analyte, the effective value of that device will be changed. So it measured based on that effective value. So you can observe here, like when we are applying the analyte, you can observe there was a reflectance change. In the first figure, it is like a peak value, and in the other figure, after the applying of analyte, and there was a slight change in that reflective value. That change itself will give the concentration of the analyte. So the other device here is surface plasma resonance based biosensor. It is very similar to the one which I discussed in the first slide, like 3-layer waveguide. The only difference is here we are using the material, and we will measure the reflectance of that biosensor. So when we are applying the analyte on that SVR based biosensor, and that analyte will react with the SVR, and when we are applying the analyte over the biosensor, it will react with the light molecules, and based on that, it will give some reflectance value. So the advantage of this is it will having the linear response, high sensitivity, and accuracy will be more for the device. The other is, so while we are moving towards the optical biosensor, we can miniaturize and we can create a lab-on-chip based biosensor. So this is the main advantage why everyone are moving towards this optical based biosensors. So coming to conclusion, today I have discussed the importance of the biosensor and what are the devices which are available in the literature of these biosensors, and even we can cascade this device, and we can generate hybrid based biosensors which will be used for remove the disadvantages as the single device, and the hybrid model will have the advantages of both the devices. Like if we are hybriding the ring resonator with this MZI, we can solve the problem of like the length of the device can be improvised. Like we can miniature, like we can create in the micrometer range. So like that we can hybrid and create the optical biosensors. And thank you for inviting me and providing me this opportunity to present about biosensors.
Thank you, ma'am, for enriching us and sharing your knowledge about biosensors and its types, characteristics, and the different applications. We are really grateful to you. I now request HOD Dr. Venkatesha M. Sir to present a token of gratitude to Kamakshi.
That's it. Here only your students are there, other students also are there. They have their student rank, subject.
They have active now.
And
But I wanted to start portaling. So they told the company after the company.
Oh,
But you send them there. Yes.
Any other college? Yes.
As we come to the end of this program, on behalf of everyone, I would once again like to thank our esteemed guests for gracing us with their presence today. We will cherish your words of wisdom and look forward to applying them. Thank you for adding immense value to our gathering today. Thank you everyone for your time and patience. I request our HOD sir to address the next session.
Good morning. Dear students, so even though you are second year students and some of the students from other colleges are here, so far whatever you have learned in the first year and second year, so it may be just a circuit learning. You might be using just K wires and few low frequency devices to see some of the sinusoidal waveforms or some small applications related to whatever you have studied. Okay, so in our college we have center of excellences that have been established by one of the startups. So it is initiated from the Indian Institute of Science Startup (NPM). So we have Photonics Center of Excellence, and one more is 5G Center of Excellence and AI. Okay, so as part of this particular program, so now we can witness so what are all the various high-end devices or high-end laboratories that they are established in our campus.